This is section 11.5. After the after chapter 11, we go to chapter 10. Chapter 10 is infinite series. And Cal 3 students often tell me that it's equally as hard, if not harder, than chapter 8. It's probably the only thing in Cal 3 that I'd say is hard, but most Cal 3 students have to really buckle down for chapter 10. So make a good grade on this first test, huh? Okay, I want to talk about area in polar coordinates. First thing is, I will do it, but if I were to ask you to do it, could you describe to someone how we found area in Cartesian coordinates? Could you? Bowers can, Travis can, William, can you? Sid? Uh-huh.
I'm not sure.
Well, you can. Trust me, you can. I just didn't describe it good enough. Josh, you know what I'm talking about? Here's what I would say if somebody asked me to do it. I'd say, if you give me a curve, I'm going to graph the curve, and I'm going to put in the boundaries of the curve. And then I'm going to divide that up into a whole bunch of very small, what?
Rectangles.
Rectangles. And a whole bunch means an infinitely large bunch of them. In fact, so many that you can't see their width, right? They're so, I'll have so many that their width you won't even be able to see. They'll be so close together. And then the stretched S. And what does the stretched S tell us to do with them?
Add them together.
Add them up. Isn't that it? Is that it? So everybody except for Travis, go home and tell your mother how to do, how to find the area under a curve in calculus. You can ask her to tell you. Okay? Then, now in polar, let me show you something. In polar coordinates, remember I'm dealing with r and theta instead of x and y, right? So forget about rectangles. You remember Cartesian coordinates, that's the XY grid. And that is, instead of calling it the Cartesian coordinate system, what's another name you've heard for it? What's another name?
X and Y.
X and Y? Or how about rectangular coordinate system? Ed, you ever use that one? Called it the rectangular coordinate, Beth, have you? I sure have. Why? Because every time you graph a point, aren't you making a rectangle? You go to the right and then up, aren't you defining a rectangle there? Well, in polar coordinates, you have angles and radii. The plural of radius is radii in Latin. You have radii, huh? So instead of dividing it up in a whole bunch of little bitty rectangles, what we're doing is we're making the slices of the pizza real small. Isn't that what that picture shows you? So what I'm going to do is I'm going to take that curve and I'm going to make pizza slices out of it. Only I'm going to make them so small that you can't see the difference between them. Does that sound familiar to you? And then what am I going to do? Add them up. And you know what add them up means in calculus, huh? So everybody get the idea? So what determines the slice of pizza? How big it is? Well, obviously the radius, right? And that is, do you buy a 14-inch pizza or a 17-inch pizza, right? Is that right? But what is the other factor that determines it?
The weight of the pizza? Or the taste?
How big your slices are, right? How big your slices are? And if I wanted to make real tiny slices, does that define a slice, my hands? If you imagine a curve that goes from fingertip to fingertip, does that define a slice? Wouldn't you make the slice of pizza much smaller by doing this? I mean, you bought a pizza that's either 14 inches or 17 inches, so all of them have the same distance out there, right? So if you want a smaller piece, don't you make that angle smaller? How small do we want to make that angle? We want that angle to be as big as the rectangle was wide. Follow? And once we do that, aren't we talking about what we did before? So do you see, I'm not going to prove anything to you, but do you see how we just applied what we knew about the rectangular system and applied it to the polar system? Now, let me ask you something. Have you ever seen this before? What is that?
Area of a circle.
The area of a circle. Suppose I want just an angle theta in the circle. Do you follow? I don't want the whole circle. I want to know the area of this little slice right here. So wouldn't I take, so for a slice over an angle theta. For a slice over an angle theta, wouldn't I say that the area of that slice is equal to the area of the circle, but trimmed down by the proportion of the circle covered by theta? So wouldn't that be the angle theta divided by 2 pi? Is that right? What part of a circle is, and let's say, for example, degree slice. Well, I told you, didn't I, in calculus, we can't talk about degrees. I want a pi over 6 slice, right? Everybody agree? So what I'm going to do, I want a 30-degree slice of a circle with radius 10. First thing I'm going to do is I'm going to find the area of the circle, the whole circle. But that's pi r squared, right? And that then is 100 pi. Am I right? Now what I'm telling you is I want to scale that down. I want to scale that down for just the little slice of pizza that I'm talking about. So wouldn't the way I would scale it down is take if my angle goes down to pi over 6, and there's 2 pi in the circle, isn't that the portion of the circle that I'm looking for? Is that right? Is that right? So wouldn't it be wouldn't the area of my slice be equal to the area of the whole circle, but the proportional area that my slice covers? Does everybody get it? William? I need to see some affirmation here. Travis? Okay. All right. But a little bit cleaner way of saying that is if I take this and divide these two out, and they do divide out, don't they? Then the area of a slice of a circle is equal to theta over 2 times r squared. Everybody get it? And that's the one I want you to remember. The area of a slice of the circle is equal to theta over 2 r squared, where theta determines the slice. Make sense to you? Now, isn't that the way we did it in rectangular coordinates? Didn't we find every little bitty, the area of every little bitty rectangle? But what defined that? The width, right? And I found the length by substituting the width in, and then I found the area of that little slice. Get the idea? Okay, so on Monday after spring break, I might remember to make this too. I think I'll put this in the slides for that Monday, but this is the takeaway message. And this is what we're going to use to find area. Have a good spring break.